assured me that you are able to see my screen.
Yeah, yes, ma'am.
Thank you. Good morning, everyone. I'm Dr. Megha from DIT University, Dehradun. So today I'm going to give you an overview about how to improve quality of software products using artificial intelligence. So first of all, I'll be starting with the introduction, then followed by basic terms, and then what can be the AI technique which can be used to improve the quality of software products. So let's begin with the introduction first. To the development of software intensive systems increasingly moves from single product to mass product development. Software product line, it is basically a set of software intensive systems. Its main aim is to share a common and managed set of features to fulfill the specific needs of a particular market segment. Now, the question is, why do we need this software product line? In order to promote reusability, to enhance quality and productivity of software products. At the same time, it will reduce the development cost and time. Now, we have the concept of software product line with us. Now, we need some modeling technique to present that software product line. So there, the concept of feature model comes into the picture. So feature model is a well popular notation which is used to describe software product line. Now, as the development and growing size of feature models, so defects may inevitably be introduced in the models. Now, we need to understand what is a defect. A defect basically is an undesirable property of relationships, and when it is going to occur, it will be occurring if the product illustrated by model does not correspond to its software product line. Now let's assume we have a product line model, but this product line model is being defective. It may have some defects in it. So when we are going to build products from this defective product line model, so these products may inherit defects in them. Now, once we have the defective products, so what will happen? It will reduce the quality of models along with the benefits of software product line. Now, before I proceed further, I would like to give a brief introduction about the background terms which will be used to understand this work. So we have feature model notations. So basically, there are three types of feature model notation that we have. One is basic feature model, other one is cardinality based feature model, and the next one is extended feature model. Now I will be discussing these feature model one by one. So let's start with basic feature model. So as the name itself is suggesting, basic feature model means it is going to tell us about the basic functionality and the structure of the model. It is a hierarchical tree-like structure which comprises of nodes and edges, where node represents features and edges represents the relationship between the features. It describes the basic relationship between the features. It represents commonality and variability in SPL. Now let's understand the terms commonality and variability in product line. So I'll take an old example of Nokia mobiles. So earlier we used to had Nokia 1100 mobile, and then we had Nokia N87 also. So in case of Nokia 1100 mobile, we had features like calling, call forwarding, messaging, and then we had the function of torch also in that. Later, when Nokia N87 was developed, so Nokia N87 had those common features like calling, call forwarding, messaging, and torch functionality. So these features will be common, and additional features like Bluetooth, camera, which were present in Nokia N87, they will be variable features. Now, after that, we have the features in the model. Now, the valid combination of these features in feature model will allow us to derive valid software products. So this was about basic feature model. Now moving towards cardinality based feature model. So as the name itself is suggesting, cardinality means we are going to have the terms min and max with it. Now, it is also a basic feature model, but it is extended with UML like multiplicities or cardinalities of the type min, max. Now here, min represents the lower bound and max represents the upper bound. The relationships introduced in this notation are feature cardinality and group cardinality. Now moving towards the third feature model, that is extended feature model. Now in case of extended feature models, we use feature attributes. Now these feature attributes provide additional information regarding the features. So this can be well understood with the help of the figure 2, which is being given here. So in case of figure 2, we can see that keyboard is a feature, which is a root feature, which is further having two child features, that is quality and walk. And now this development time and this cost, they would be the attributes for all the sub features of keyboard feature. So this is extended feature model. Now, figure 3 represents the feature model of laptop system. As I earlier mentioned, that feature model is basically a hierarchical tree-like structure which comprises of nodes like laptop, hardware, software, and so on. And edges represent the relationship between these features. Now, in case of this feature model of laptop system, laptop is the root feature, which is further having two child features, that is hardware, and then we have software, and then hardware and software, they have their respective child features. Now, this feature model is being created with the help of various relationships which are mentioned in the table below. So here you can see that column 1 represents some notation and column 2 represents the description of the relationship, and then column 3 represents the example of the particular notation by using this particular feature model. Now let's start with the first notation. So as you can see, we have first notation as mandatory. In case of mandatory, child feature C must be included in all the valid products whenever its parent feature P is included, and vice versa. Now let's understand this particular notation with the help of the example over here. So here you can see hardware is mandatory to be included whenever laptop is included. So this is mandatory relationship. Now let's talk about the second relationship, that's optional. So here you can see P is the parent feature, C is the child feature. So child feature C may or may not be included in all the valid products associated with its parent feature P. And the example is, here you can see camera. It is an optional feature, but is optional to be included whenever hardware is selected. We may or may not include it. And then we have third type of relationship, that is alternative. So P is the parent feature, C1 and C2, they are the child features. Alternative means only one child feature has to be selected. So child features C1 and C2, they are in alternative relationship with their parent feature P, when exactly one of the child features has to be included to develop any valid product whenever P is included. Now let's understand it with the help of the example. Here we have software for laptop. It may include support for Linux and Windows. You can see here Linux and Windows, they are in alternative relationship with operating system. So whenever operating system is selected, so out of Linux and Windows, only one can be chosen. Now, we have another relationship, that is OR relationship. Again, P is the parent feature, C1 and C2, they are the child features which are in OR relationship with parent feature P. Now, child feature C1 and C2, they are in OR relationship there with their parent feature P when one or more child features are included. Means you can include C1 or C2, or you can include both. Now, let's understand again with the help of the example over here. So whenever application is selected, so what can be chosen? You can choose Skype, or you can choose internet browser, or both can be chosen in the valid product whenever application is being selected. Now, there are two types of cross-tree constraints. One is your implication, another one is exclusion. Now, C1 and C2, they are child features. Now, features C1 and C2, they are related with implication constraint. Represent that C2 should be included in all the valid products whenever C1 is chosen. Now, in case of exclusion, features C1 and C2 related with exclusion constraint cannot be included simultaneously in same valid product. Now, we have understood the terms which are being used to create a feature model. Now, our main agenda is to identify the defects in software products, because in industry, having the quality software products is of utmost importance. So let's understand the types of defects first. So your column 1 represents the type of defect and column 2 describes the corresponding description of the defect. Now let's start with the first one. So first defect is redundancy. A relationship modeled in several ways, it lead to redundancy in feature model. Let's understand with this notation. P is the parent feature, C1 is mandatory. Means C1 has to be included whenever P is included. C2 is optional, means it may or may not be added. Then we have implication relationship from C2 to C1, means whenever C2 is chosen, C1 has to be by default there in the product. So like C1 is occurring 2 times, being mandatory and because of this relationship. So this case leads to redundancy defect. Now we have another type of defect, that is dead feature. Now, a feature that despite of being defined in the feature model, but it will not appear in any valid software product. Again, C1 is mandatory, C2 is optional. C2 is present in feature model, but because of this exclusion relationship, only one child feature can be selected, either C1 or C2. So in that case, C1 is mandatory, so it will be chosen, and C2, although it is there in the feature model, but it will never be a part of any valid product. So it will become dead feature. Now we have third type of defect, that is false optional feature. A feature is declared as optional in the model, but it is present in all the products of the software product line. So here C1 is mandatory, means it has to be there in the valid products. Now C2 is optional. Although C2 is optional over here, but we can see that we have an implication relationship from C1 to C2. It means whenever C1 is chosen, so C2 has to be there in the valid product. So even C2 is optional, but it will be a part of all the valid products. Now moving towards the last effect, that is inconsistency. Inconsistency, as the name itself is suggesting, means some contradiction would be there. So the contradictory information in the model is defined as an inconsistency. So once you have inconsistency in the model, so what is going to happen? It will definitely hinder the derivation of valid products from the model. So like C1 and C2, they are mandatory child features, means they would be a part of valid product. But as we can see that there is an exclusion relationship between these two child features. So it means that due to this exclusion relationship, these two mandatory features cannot be the part of valid product at the same time. So these were the various types of defects which will be dealt in this work. Now, as I mentioned, what is redundancy defects? So based upon that, these defects due to redundancy, they have been categorized into 6 categories, 6 cases. So first case includes the redundancy because of exclusion and group cardinality. Case 2 includes the redundancy defects which occurs due to mandatory feature and implication. Case 3 includes redundancy due to multiple implications. Case 4 includes defects due to redundancy, but because of the multiple exclusions. And case 5 includes redundancy due to cyclic implications. And last one, it includes defects due to transitive implications. Similar way, from the existing work, we came to know that the defects due to that feature can further be categorized into 4 cases. Case 1 would include the defects due to that feature, which is basically occurring due to mutual exclusion between full mandatory feature and optional feature. Now, if I talk about case 2, it will include the defects due to that feature due to implication and exclusion. Case 3 will include dead features which occurs due to implication and group cardinality. Now, last case will include dead features which is going to occur due to exclusion and group cardinality. So this was about the dead features. Now we have defects due to false optional features. Now, based upon the literature that we have, these defects have been categorized into 4 cases. So case 1 would include false optional features which are occurring due to implication between full mandatory feature and optional feature. And case 2 will include false optional features due to implication and exclusion relationship. And case 3 will have defects due to implication and group cardinality. Similarly, case 4 would be having false optional features due to exclusion and group cardinality. Now we have the last effect, that is inconsistency. Inconsistency means what? Contradictions in the relationships. So these defects have been further categorized into 4 cases. So first case includes the inconsistencies which occurs due to implication and exclusion simultaneously. And case 2 would include defects due to inconsistency because of mutual exclusion between mandatory features. Now, if we see case 3 includes inconsistency due to implication and exclusion cross-tree constraints. And case 4 will have inconsistency due to implication between the alternative child features. So these were the various cases for different types of defects which have been identified from the literature itself. Now let's understand. See, now we have understood what is software product line. We have understood what is feature model, how feature model is being created, and then what are the types of defects which may occur in software products, which reduces the quality of software products. Now let's understand these defects with the help of running example over here. So as all of you can see, that figure 8 represents the feature model of a laptop system for explaining defects. As I already mentioned here, laptop would be the root feature, hardware and the software, they will be the child features of laptop. Now let's understand dead feature concept first. So you can see operating system is mandatory feature, means it will be a part of the valid product. And application is optional feature, means it may or may not be a part of valid product. But we have exclusion relationship between mandatory and optional feature, which means that only one can be chosen in valid product. So operating system will be chosen because it is mandatory, and this optional feature will become dead feature, although it is there in the feature model, but it will never be a part of any valid product. Now, moving towards next type of defect, that is false optional feature. So this rectangle box, you can see this represents a case of false optional feature. So what is going to happen? Operating system is a mandatory feature which is having child features as Linux and Windows in alternative relationship. Alternative relationship means only one child feature can be chosen, either Linux or Windows. Now, USB port is having mandatory, means it will be a part of the valid product, but we can see that there is an implication relationship from USB port to Linux, means whenever USB port is chosen, Linux would be by default, it will be chosen. So Windows will be left over. It is an optional feature. It will be left over. And then this Linux is also an optional feature. However, because of this implication relationship, this will not be optional anymore because it would be a part of valid product. So this Linux will become false optional feature. Now let's understand what is redundancy over here. Now, please focus upon this rectangle shape over here. So we have 3 features over here: screen and high resolution. They are mandatory features, and camera is an optional feature. So we can see that there is an implication relationship from screen to camera, means whenever we are going to choose screen, so camera has to be a part of that valid product. Now, you can see that high resolution is also a mandatory feature. So means whenever we are going to choose this high resolution, there is an implication on camera, means camera would be chosen again. So this is the case of redundancy because this camera is appearing twice in that valid product. So this is redundancy defect. So with the help of this running example, these 3 defects were being explained. Now, we have understood that what is the problem, what kind of defects that we have in feature model, and how they can deteriorate the quality of the software products in industries. Now, a framework has been given to handle these defects in software products. Now, this framework has been divided into 3 stages mainly. So stage 1, it includes transformation of feature model into predicate-based feature model ontology. Means we have the model, but we are going to convert it into ontology. Now, there is a repository known as plot repository. So the models are being available on that repository. So the model is available on plot repository in the form of SXFM format, means simple XML format. Now we have a feature ID tool. Now this feature ID tool will import this feature model in simple XML format. Now feature ID tool will convert that simple XML format to XML format. Now an XML parser is being developed because our main agenda is to convert that model into ontology. Then only we can do the processing. Now XML parser is being developed, which converted model from XML format to ontology, first order logic based ontology. Once the ontology has been generated, now as a part of stage 2, first order logic based rules were developed and these rules were applied on the generated ontology. Now as a part of stage 3, the results were obtained and the results included identified defects with their causes and solutions, how to resolve these defects. So this is about the framework, that how it broadly works. Now, let's understand the methodology behind this framework. So as I mentioned, the model is available on Sprout repository. So first point is to analyze that model and then injecting features and cross-tree constraints in it. And then we have to transform that model into ontology. And then we are going to develop first order logic rules, which will be applied to that generated ontology so that we can get the results, and the results will include identified defects with their causes and what should be the solutions to resolve these defects. Now, this entire methodology has been explained with the help of a case study. So as we can see that this figure 9 represents e-commerce system 1 feature model representing defects due to redundancy. So here we can see this e-commerce system, it is the root feature, which is further having child features as manufacturer's catalog and product catalog. And then we have further sub-child features for each of the feature. And now please focus on these rules over here. So this particular case, that is rule.r1, this represents the case for redundancy 1. Now rule r.2, this particular case represents the case of rule r2, defect 2, redundancy 2. Now rule r.3 over here, it represents the case of defect 3, redundancy 3. And then similar way, we have 17 types of redundancy defects which has to be dealt in this work, and these R.1 till R.17 represents each redundancy defect. So this is a case study which is being taken up, and now once you have the feature model with you, now what we need to do, we need to convert that feature model into ontology. So obviously we are using AI technique, so there should be few rules to transform a model from one format to another format. For that, few transforming patterns have been developed, which is going to convert model into predicate-based ontology. Now this table represents what are the patterns, or we can say what are the rules which are used for the conversion of model into ontology. Now, column 1 represents the name of the relationship, and column 2 represents the feature ID representation, means how this relationship is being graphically shown in this feature ID tool. And column 3 represents the feature model representation. And then correspondingly, ontology has been generated for that particular relationship. Now I'll just explain few. So let's take the first one. That's an optional relationship. Now, in case of optional relationship, we can see how it is being represented in feature ID. So this is the notation in feature ID, and this is the notation for feature model. Now, this particular notation of feature model has been converted to one predicate in ontology, that is F, then bracket, feature underscore 1, comma O. Now, what does it mean? It means that feature underscore 1 is an optional feature. O stands for optional, M stands for mandatory. So if I talk about this particular figure, it is saying that feature underscore 1 is an optional feature. Similar way, we have mandatory feature, which is being presented in feature ID like this, and then this is the representation in feature model. Now, how are we going to convert into ontology? F will be there, and then we have these values as feature underscore 1, comma M and bracket close. Now, how are we going to interpret it? It says that feature underscore 1 is a mandatory feature, and M represents the mandatory. Now, we have third type of relationship, that is parent. Now here we can see feature underscore 1 and feature underscore 2. Like feature underscore 1 is the parent of feature 2. Similar way, we have the notation in feature model as well. Here feature 1 is the parent, feature 2 is the child. Now the main agenda is how to convert it into ontology. So again, we have P as the relationship, feature underscore 2 and feature underscore 1 will be the values. Means feature 1 is the parent of feature 2. So at first place, we have written the child, and at the second place, we have written the parent. Now, understand the relationship exclusion, that how it will be presented in ontology. So this will be the presentation in feature ID tool. This is the presentation in feature model. Now, this same would be transformed into ontology over here. So E stands for exclusion relationship. Feature underscore 1 is the one at value, and feature underscore 2 is another feature. Now, what it signifies? It signifies that feature underscore 1 excludes, because E stands for excludes feature underscore 2 with exclusion relationship. Similar way, we have implication. It is the feature ID presentation. That's the feature model presentation. Now let's convert it into ontology. I stands for implication. So what this complete notation is signifying? It is signifying that feature underscore 1 implies feature underscore 2 with implication relationship. Similarly, we have group cardinality, as I mentioned in the first slide itself, that the group cardinalities include your alternative and or relationship. Now, alternative relationship is being shown like this. As I told you earlier, alternative means you are going to select only one child feature. You cannot select two child features in valid product. So C represents cardinality over here. Feature 1 represents the parent, and feature 2 and feature 3, they are the child features which are in alternative relationship. Similar way for or relationship means you can select feature 2 or you can select feature 3, or both can be selected in valid products. So C stands for cardinality. Feature underscore 1 would be the parent feature, feature underscore 2 and feature underscore 3, they will be the child features, and the cardinality will be 1 up to maximum will be 2. So these were the rules which will be used to convert model into ontology. Now, after following these patterns or after following these rules, this will be the feature model ontology which will be generated. So figure 10 represents feature model ontology of e-commerce system 1, where F represents the features over here and P stands for the parent relationship, I stands for the implication relationship, and E stands for exclusion relationship, and C stands for cardinality relationships, which were discussed in the previous slide. Now, we have got the ontology with us. Now, what is going to happen? Once you have the ontology with you, after that, our next step is to develop first order logic rules. We need rules to apply on this ontology so that we will get some results. Now, these rules are developed in first order logic and then they were applied on the generated ontology. After applying these rules on the generated ontology, so these are the results which are obtained. So figure 12 represents the results attained after implementing rules to e-commerce system 1 ontology. So here we can see as a part of the results, we can see that your results will include defect. What is the defect? Its cause and correction. So for example, your first defect is redundancy 1. And what is the cause behind that defect? Why it occurred in the model? Exclusion. The cause was exclusion between alternative child features A2 and A3 is redundant. And what will be the solution? Eliminate exclusion 1. Means a suggestion has been given, a solution has been given to resolve that particular redundancy. Similar way, in case of second, the defect will be redundancy 2 and cause would be multiple exclusion of an alternative child features A6, and the solution would be eliminate exclusion relationship. In similar way, for defect, redundancy 3 will be the third defect. And what is the cause? What is the source for this defect? Optional feature A11 implies the full mandatory feature A10 is redundant, and the solution to fix this defect would be eliminate implication. Similar way, because we have considered 17 defects for the redundancy. So when we are going to execute these rules on the generated ontology, so we will be getting the results for each and every defect, which will include what is the type of defect, identify defect, what is the cause, what is the source behind that defect, and what should be the solution to resolve that particular defect. Now, as all of you must be aware that see, whenever we do some work, so obviously we need to evaluate that method, right? So in order to evaluate that method, we should have some evaluation metrics. We need to evaluate that method with some evaluation metrics. So one of them is accuracy. It plays an important role because what it will be doing, it is going to provide the accuracy of the identification of defects, their causes and corrections. Now, this accuracy would be calculated how? By the number of identified defects, with their causes and correction. See, these are the identified defects which we have come to know after implementing this method, along with their problems, along with their solutions. By total number of defects with their causes and corrections in model. Like how many number of defects were there in the entire model? So after doing this computation, we will be getting the accuracy of the method. Now, once we have calculated the accuracy, the results conclude that the approach has identified 100% of the defects with their causes and solutions in all the models. Now, accuracy has been calculated. Again, we need to check out that what is the scalability. So what we will do, we are going to calculate the computational scalability. So figure 13 represents execution time, which is required by all the rules per number of features to deal with all defects. So let's focus on this graph now. So x-axis represents the number of features over here. Y-axis represents the time in seconds. And this particular graph shows that how much time was taken by the rules to deal with all defects. And the results conclude that the queries take a reasonable time of 0.551 second to deal with defects in large models up to 30,000 features. Means this method is able to give quite an efficient result with large models as well. Now, whenever we are going to do the experimental results, so obviously we have to take care of many parameters which may affect the experimental results. So one of such parameter is number of features and cross-check constraints. What is cross-check constraint? That implication and exclusion only. So here figure 14 represents the execution time required by all the rules in models. Now let's see here. Plot number A, what it is going to represent, it tells about the number of features. Plot B represents the number of implications. Plot C represents the number of exclusions. And D represents number of implications and exclusion in 1:1 ratio. Now, here we can see this sky blue color, it represents the mandatory features. This red color represents optional features, and this purple color, they represents mandatory and optional features in 1:1 ratio. Now, the results conclude from these graphs, what we can conclude is that as an overall trend, mandatory features, the sky blue color line, they represent mandatory features. They improved performance, whereas mandatory and optional features, that is purple color line, in 1:1 proportion deteriorated in all cases. Why it deteriorated? Because it is taking a lot of time for the processing and to identify the defects. On the other hand, the sky blue color line, which represents your mandatory features, takes less time to identify the defects. So it is going to improve performance. Similar way, there is another parameter, height of the tree bed, because as I mentioned you, that feature model is a hierarchical tree-like structure. So height of the tree will also play an important role. So figure 15 represents the models in combination with A represents the number of features, B represents the number of implications, and C represents the number of exclusions, and D represents the number of implications and exclusions in 1:1 ratio. Now, what has been done here, like for all the trees, different levels of the tree were considered and different number of features were considered to check the feasibility of the work. Now, execution time required by all rules as per the height of the tree. And what were the levels which were considered? 10, 20, 30, 40, and 50 in the models, with variation in features, that is 1,000, 2,000, 3,000, 4,000, and 5,000 respectively. Now, from these plots, from these graphs, what is the conclusion? What is the inference? As an overall trend, mandatory features, which are again represented by sky blue line in all the plots, sky blue color. So mandatory features are going to improve the performance. Now, there is another parameter which plays an important role for the experiments, that is number of alternative and or relationships in feature model. Alternative, I has already mentioned that only one child feature has to be chosen. In case of all, you choose either one or two or both can be chosen together. Now, what this figure 16 represents? This represents models in combination with A represents number of features, B represents number of implication, C represents number of exclusion, and D represents number of implication and exclusion in 1:1 ratio. Now, execution time required by all rules with increasing alternative and or relationship in 1:1 proportion, that is 500, 1,000, 1,500, 2,000 and 2,500 relationships in model. Means you have feature models. Now, what are we going to observe? We are going to see that what kind of results we are going to obtain when there will be a variation in alternative and or relationships in models, along with the variation in features. That is 1,000, 2,000, 3,000, 4,000, and 5,000 respectively. Now, after the execution of these rules and the graphs that we have received, what is the observation? That as an overall trend, mandatory features, again, which is being represented by sky blue color line, has improved the performance of the work. Now, the most important part of any work is to compare your results with existing works. So here column 1 represents that what is the article, and column 2 represents description of features, constraints, and defects. Means number of features, constraints, and the defects which were considered in that work, and then defect type, that feature, false optional, inconsistency, redundancy, and total rules. What were the rules developed by those authors, and number of rules per defect type, and then execution time by the existing work and our proposed work. So I will just explain briefly one or two works from this. So let me see this one first. Yeah. So if I talk about Al-Faqih et al. So what have they done? They have considered 20,000 features in their work. And what is the type of defect they have dealt with? R stands for redundancy, T stands for dead feature. And how many rules they have developed? 13 rules were developed by these authors. And after these 13 rules, 9 rules were used to identify redundancy defect and 4 rules were developed for dead feature. Now, existing work like Al-Faqih et al. Authors, they have utilized 2 to 1.516 seconds to identify the defect with cause. The same experimental setup was created and the proposed method was applied on it. And then defects were identified with cause in 0.058 seconds and defects were identified along with cause and correction in 0.07 seconds. So you can see a huge difference between the execution time and the performance times to identify defects in the previous work and in this proposed work. Similar way, we have Kowal et al. Now, in case of Kowal et al., what has been done? 2,513 features were used. 2833 constraints were used. 563 redundancy defects were there in the models. 192 dead features and 12 false optional features were there. So 3 types of defects were being dealt: redundancy, dead feature, and false optional feature. Rules were not developed, and then the time taken by the approach was 16,546.44 seconds. On the other hand, same set of models were used for the implementation of our work, and the time taken by our model was 3.475 seconds. Now, the last one is the proposed method, the AI technique, which is being used to deal with defects in software products. So 30,000 features were considered: redundancy, dead feature, false optional feature, and inconsistency. These are the types of defects which were being dealt in this work, and 75 rules were developed, where 17 rules were created for redundancy, 20 were created for dead feature, 17 were created for false optional feature, and 12 were created for inconsistency. Now, the time taken by the rules to identify redundancy defects were 0.185. Similar way, for dead feature, it was 0.187. For false optional feature, it was 0.265. And for inconsistency, it is 0.16. When we applied these rules combinedly on the model, so the total time taken was 0.551 seconds. So we can see a huge difference between the results that have been obtained with the proposed method and with the existing works. Now, let's talk about the conclusions, that what we have understood from this work. So first thing is that we had model in the repository, but we had to convert that model from one form to another. And why we have converted? Because we wanted to formalize, we wanted to give it a structure so that it can be used for further experimentation. So first thing is formalize model from an ontological viewpoint by transforming it into a predicate-based feature model ontology. Fine. Now, once ontology has been generated, what has been done? Automated identification of defects with their causes and corrections. Now, the benefit of this work is that these causes and corrections which were obtained in the results, they were explained in a user-friendly natural language so that it can be easily understandable by product line developers, which will assist them to resolve defects. Next one is improve performance and scalability. The results indicate that the technique is effective, accurate, and scalable. Why it is scalable? Because it can handle defects in large models up 30,000 features in a reasonable time of 0.551 seconds. And the most important, why this work has been done? Because to improve software product line in terms of reusability and quality. Identified and resolved defects in early development process of model. It allows defect-free valid software products from product line by subsequently improving the quality and reusability of models in SPL. This concept of software product line is being utilized in large companies like Samsung, Motorola, and Nokia has also utilized it. Even Microsoft is also using it. And one of the product line for Microsoft is Excel sheet. You can have Office is one of the product line. So this is all about this work. These are the references which are being utilized for this work. That's all. Now I would invite my audience if they have any query regarding the same.
Yeah, thank you so much, ma'am. Very elaborate session. Thank you so much for telling in detail. So I'll open the dice for the participants. So if you have any queries, you may please ask Meha ma'am right now. Any queries? And kindly please raise your hands and I'll just unmute you because and there's no chat as well. So kindly raise your hands for any queries. Okay. Yeah, we could see the reactions from them. Fine. Okay, ma'am. So I don't think there's any queries from the participants end. So with that, I would like to take my chance to thank you so much for your wonderful presentation and time. Like very big appreciation for your energy for keeping it throughout the session. And thank you so much, ma'am. Like one other thing, like ma'am's doing the second time session for us. I mean, considering the very good appreciation from the last time participants, when we requested ma'am for the second session, and she very gladly appreciated. And thank you again for that, ma'am.
Thank you, Dr. Meena, for providing me this opportunity again. And I would like to be the part of these FDPs in future as well. And
Yeah.
thank you, audience, for listening me with patience.
Okay, ma'am. Thank you so much, ma'am.
Okay, have a good day.